Hello everyone, welcome to this video. In this video, we'll be looking at Cauchy's theorem for abelian groups. Now, what is this theorem? This theorem tells us that if we have G as some finite group, which is also an abelian group, right? So that means commutativity holds within this group. Now, if we take some prime number P with us, right, such that this prime number P divides the order of the group G, right? P divides the order of G. Then we have to prove that the group G has at least one element of order P, correct? So here, in order to prove this result, we will make use of factor groups that we have studied and induction, and we will be applying induction on the order of the group, right? This is a natural number, so we can apply induction onto this number, correct? So for applying induction, what we assume first of all that G is a finite abelian group and P be a prime number that divides the order of the group. This thing we are assuming, and we have to prove that G has an element of order P with us, right? So in order to prove this, we will apply induction, as I've told you, on the order of G. So if the order of G is the lowest, which is say 2, why? Because in that case we can prove that it has an element of order 2. Then the given prime P would be 2, because we are assuming G to be a finite abelian group and that P be a prime that divides the order of 2, and you see only 2 divides the order of 2, right? So P is 2, so that means the group should has an element of order 2. Let's say the element is A, right? So if that is the case, then G would have two elements. One should be the identity, other one is non-identity element, which is not equal to E, right? We take it to be such that this is a group. Now, if this is a group, then that means the closure property as well as the existence of identity that we have already took, the existence of inverse and associativity, all such properties should be there here, right? So that means if you apply the closure property onto A, so A into A should also be present in G, but we only have two elements here. One is E, another is A, right? If you have A square is equals to A, by the cancellation law, you have A is equals to E. This is not possible because we have taken them to be distinct elements, right? So therefore, we should have A square is equals to E. So that means the order of A should be equal to 2 here. So hence, in this case, the result is proved, right? When the order of group is 2. Now what we do, we assume that the result is true for all the groups of order which are having order less than the order of group, right? So this is what is there if the order of group G is n. So we are assuming some group G dash such that its order is less than n, right? So what does it mean? It means our hypothesis now becomes if we have some group G dash such that the order of G dash is less than the order of G, and we have some prime number P dividing this order of G dash, right, this group, then this group G dash would definitely contain an element of order P. This is our supposition. This is our hypothesis. Now using this hypothesis, we shall be proving the result for the order of the group, right? So here we wanted to prove that G has an element of order P, right? G has an element of order P. This is what we wanted to prove. So here we first of all show where P is some prime number, right? Instead of P, we say G has elements of prime orders. It could be any prime number, right? So for proving this thing, let us suppose it has no element of prime order. Then what would happen? So if you have some element X within G, then the order here would not be prime and it would be some composite number. So it would be the product of two numbers such that at least one of them is prime, right? Because you know the property of composite number, you can decompose them into the product of primes. So we assume at least one of the number is prime. So we are assuming Q is prime. So because M is the order of X, so that means X raised to power M is E, right? What is M? M is Qn. So X raised to power Qn is E. So you can write this to be like this: X raised to power N whole raised to power Q is E. So that means the order of this element is Q, right? What is this element? X raised to power N. So here Q is a prime number. This we have already defined. So that means if x belongs to G, by the closure property x raised to power n should also belongs to G. So that means G now contains an element x raised to power n which is having prime order, right? Its order is Q. So we say G has elements of prime order within it. One thing is proved. Now we have to prove in particular that the order should be P, right? So here we found an element x such that its order is Q. Right now you would say we have found x raised to power n. How did this x appear? We are assuming, because this was some arbitrary member, so we can assume this to be x which is an element of G to have some prime order Q. Right now, if this prime number is exactly equal to P, right, then our result is proved, because that is what we wanted to prove, that G has an element x of order P, right? If it is not equal to each other, if it is not equal to P, Q is not equal to P, then we can use this result that every subgroup of abelian group is normal. This is the result, right? So that means the subgroup which is, we took x from G, so we can construct a subgroup from it, right? So this subgroup we say is normal. If this subgroup is normal, so that means the factor group which is constructed from this group would be the quotient group, right, of G. So let's call that quotient group by G bar. So G bar is your G which is created from this subgroup generated by X. So because the group G is given to be abelian, hence the quotient group formed by is also abelian, because we have this result that quotient group of abelian group is abelian, right? So that means G bar is abelian, and here you see P divides the order of G bar. Why this is so? Why we are highlighting these assumptions? Because these would be the assumptions of the hypothesis that we are going to use by the way of induction, right? Now that is clear how G bar is abelian. Now we have to prove P divides the order of G bar. Let's see how. What is the order of G bar? It is the order of G divided by the order of the subgroup generated by X, and you know what is this order? This order is Q, right? If this order is Q, then you see, because P divides the order of the group G, right? So it would definitely divide the order of group G bar. Why? Because G bar is the order of G divided by Q, and Q is some prime number. So definitely P would divide this order as well. So here we have both these assumptions. Now you can look at your hypothesis here. If you have the order of G, some group less than the order of group G, and P divides its order, then that group would contain an element of order P. So here we are saying similar thing, that G bar is an abelian group such that P divides its order. Then this group, by the hypothesis, G bar would contain an element of order P, right? Now what form does the elements of G bar consist of? How they look like? They are cosets, right? They are cosets. So for defining cosets, we take some element y from G, and because we use this subgroup to generate the quotient group, so the quotients would look like y the subgroup, correct? So if this is the element which is having order P, by the definition of order, you can write y, the group generated by x raised to power P, is equals to E, right? So what does it mean? It means that you can further simplify the results using the properties of cosets. You can write it like this, correct? Now what does it imply? It implies either y raised to power P is identity, or y raised to power P would belong to the subgroup which is generated by X. In the first case, if y raised to power P is E, that means the order of y is P. So that means G has an element y of order P, correct? If y raised to power P belongs to the subgroup generated by X, so that means y raised to power P has order Q. Why? Because the order of this is also Q, and any element within it would have the same order, right? So you can write y raised to power P raised to power Q is equals to E, because y raised to power P has order Q, right? So you can shuffle the powers like this, y raised to power q raised to power p. So that means now y raised to power q has order p, right? So this is it. And if y was some element from which was taken from G, then y raised to power p would also be taken from G and q, right? And now this y raised to power q has order p, right, and it belongs to G, hence we can say that G has an element of order p within it. And this is what we wanted to prove here. So I hope you understood the proof of this theorem well. Well, that is it for this video. Thank you for watching.